In this section, we will talk about how the annual yield varies depending on the number of compounding periods in the year. An important concept here is that of periodicity. Periodicity refers to how often compounding takes place. For a coupon paying bond, the concept is straightforward because let's say you have a bond which pays a coupon every 6 months, then the periodicity is 2 because we compound twice in a year. If a bond has 4 coupon payments in a year, in other words every quarter, then the periodicity would be 4. But what do we do with a zero coupon bond? Here the periodicity is arbitrary. So depending on the periodicity we use, the stated annual rate will be different. Let us work through this example which is from the curriculum. Consider a 5-year zero coupon bond priced at 80 and the par value is 100. What is the stated annual rate for periodicity equal to 4? If periodicity is 4, we are assuming that compounding happens 4 times every year, which means that over 5 years the number of periods is 5 times 4, which is 20. So we have 20 periods. You can think of this as 20 quarters, or every quarter is a period. Now we can come up with the yield for 1 quarter. How do we do that? We can set n equal to 20. The interest rate is what we are computing. The payment is equal to 0. The PV is equal to minus 80. FV is equal to 100. And let's come up with I. The interest rate we come up with is 1.12%, which is for 1 quarter. To annualize this, we multiply by 4 and come up with 4.49. This is the stated annual rate assuming a periodicity of 4. What happens if the periodicity is 2? Then we change n equal to 10 because we'll have a total of 10 6-month periods in a year. When you do the calculation for n is equal to 10 or periodicity equal to 2, what you will get is 4.51%. And if we assume a periodicity of 1, then you will get 4.56%. Notice something interesting here. We are going from 80 to 100, but depending on the periodicity, the stated rate is different. If the periodicity is high, as we have in this case, then a lower stated rate gives us the same effective return as this. So 4.49 with periodicity of 4 is equivalent to 4.56 with a periodicity of 1. Now if you get an exam question where you are told that there are two bonds, one has a periodicity of 4, the other has a periodicity of 1, and the stated annual return for both bonds is 4.49. Which one is better? And the answer obviously is the bond with a periodicity of 4, because there effectively you will be getting a higher return. We are assuming that all else is equal. There are two more terms that I want to make sure you know. Effective annual yield, this is the stated rate where periodicity is 1, so that would be this number. Since most bonds have a periodicity of 2 because they make 2 coupon payments a year, that is an important term, and that is referred to as the semi-annual bond equivalent yield. And the application of this is that you are comparing a zero coupon bond with a bond which makes a payment every 6 months. What you would then want to do with the zero coupon bond is use a periodicity of 2. then the number that you come up with can be compared with a coupon paying bond where the payments are made every 6 months. Let's now work through example 7. A 5-year 4.5% semi-annual coupon payment government bond is priced at 98. We need to calculate the annual YTM stated on a semi-annual bond basis. In other words, we need to calculate the yield for a 6-month period and then multiply by 2, which will give us the annual YTM. A 5-year bond, given that we have 2 periods per year, means that n is equal to 10. The interest rate is what we are trying to calculate. The payment is equal to 4.5 divided by 2. The present value is minus 98 and the future value is equal to 100. When we compute I, what we should get is 2.48%. This is for a 6-month period. To come up with the annual number, we multiply this by 2, which will give us 4.96. So that is the answer to this first part. Then we come to part A. Convert that annual yield, so convert 4.96 into an annual rate that can be used for direct comparison with otherwise comparable bonds that make quarterly coupon payments. I'm going to do this slightly differently from what the curriculum has done, and I think my method will make this more intuitive. What have we calculated up here? What we have said is that for every year, the year can be broken into 2 parts, and the yield for each period, so we have 0, 1, 2 periods per year, the yield for each period is 2.48%, or in decimal terms it would be 0.0248. This means that $1 invested at the start will become 1.0248 squared at the end of the second period, or at the end of the year. If you do this calculation, you get 1.0502. Now, what is the quarterly rate which will give us the same answer? And here is how I suggest you think about it. Same 1 year, but now broken into 4 periods. So what is the rate for this quarter? Let's say that the rate is X, and we again start with $1. What you can say is 1 plus X to the power of 4 is how much you will have at the end of the period. To make this equivalent to a scenario above, this must be equal to 1.0502. Now you can do the maths. Just take the 4th root of this and the 4th root of this, and what you will then have is 1 plus X is equal to 1.0123. In case you don't know how to do the 4th root on your calculator, there will be a y to the power of x. Just plug in 0.25 for x. This means that x is equal to 0.0123, and the interpretation is that the rate for 1 quarter is 1.23%. The stated annual rate will then be this number times 4, which is 0.0493. In percentage terms, we can say that the stated annual rate with a periodicity of 4 is 4.93%. In other words, a rate of 4.93% given a periodicity of 4 is equivalent to a rate of 4.96% with a periodicity of 2. And this makes sense given what we talked about on the previous slide. Here we have a higher periodicity, so a lower rate, a slightly lower rate gives us effectively the same result. What about part B? In my method, we have actually already done part B, an annual rate that can be used for direct comparison with otherwise comparable bonds that make annual coupon payments. So if a bond makes an annual coupon payment, then a rate of 5.02% will be equivalent to the two rates that we have talked about over here. We'll say a little bit more on yield measures before moving on. Remember, YTM is essentially an IRR. The internal rate of return depends on cash flows and the exact timing of the cash flows. So let's consider a situation where a coupon payment is slated for 15th March 2015. But it turns out that this is a Sunday. So the coupon payment won't actually be made on this day. It will be made on the following Monday. So what convention do we use in coming up with the IRR? Do we assume that the payment is actually made on this day, or do we assume that the payment is made on Monday? Two conventions can be used. One is called the street convention and the other is the true yield. The street convention is to assume that the payment is actually made on the date stated, which is 15th March. The other convention is called the true yield convention, where we assume that the payment is made on the Monday. So this is called true yield because this is the actual true yield, as it makes the correct assumption. But you can imagine that this is tedious because we need to figure out exactly what holiday and what weekend date might coincide with coupon dates. So the street convention is to simply assume that if a coupon payment is on 15th March, then the payment is indeed made on 15th March. This is a subtle difference. The number that will be calculated is not going to be very different. However, if the notional principal is huge, then in percentage terms, even though the number differential is small, but in absolute terms, it can be substantial. Another convention is the government equivalent yield. This assumes a 360-day convention. And you also need to know this term, current yield. You have seen this in other places. The current yield is the coupon payments over the next 12 months divided by the flat price. Now let's take a look at example 8. Here I'll simply explain what needs to be done, and then you can do the calculations and double check with the curriculum. Confirm the calculation of the two yield measures for the two bonds. Let's take bond A, and we are given the current yield. The current yield is simply the coupon payments over the next 12 months, which would be 4 and 4, that is 8, divided by the quoted price, which is the flat price, or 90. So 8 over 90 will give us this number. For YTM, you can use the calculator method. So just plug in the numbers. The maturity is 5 years. So N is going to be 5 into 2, which is 10. Plug in a PV of minus 90, FV of 100, payment equal to 4, and then you will come up with a 6 monthly YTM. Multiply that by 2 and you will come up with this number. You can use the same procedure over here, but note that this is quarterly, so the number of periods is going to be 5 into 4, which is 20. Part 2. The analyst believes that bond B has a little more risk than A, which means that the YTM on B should be more than the YTM on A. How much additional compensation in terms of a higher YTM does a buyer of bond B receive for bearing this risk compared with bond A? The quick thing to do, and this is something that you might be tested on the exam, would be to simply look at the difference of these two numbers. but that would not be correct because we are not comparing apples to apples. A is semi-annual, B is quarterly. What we need to do is convert quarterly into semi-annual as we did in the previous example. And when you do that, on a semi-annual basis, the yield is a little bit higher. It is 10.839. This number now can be compared with 10.630. You find the difference and what you get is 20.4 basis points. So that is the compensation for taking additional risk. Let us now go over a few more yield measures. And to understand these yield measures, I'll take a very simple example. Let's say we have a 10-year bond which makes a coupon payment every year. The par value is 100, and let's say that initially this bond sells at par value, so you pay 100. The coupon payment that you will receive every year is 10. Let's say that this bond has 5-year call protection, and at the end of 5 years, the issuer has the option to call the bond back by paying 102 or 102% of par, and then at the end of year 8, the issuer can call the bond back by paying 101% of par. What is the yield to first call? To calculate this, you assume that the bond will indeed be called over here. So you do your simple calculation. You plug in the PV equal to minus 100, use N equal to 5. The payment is 10, the FV is 102, and you compute the yield. That will be the yield or the interest rate associated with the first call, and that's called yield to first call. Then you can compute yield to second call, where we use N is equal to 8, and the FV now is 101. So you can come up with the yield to second call. With YTM, you assume that the bond is held to maturity. Yield to worst means that you take the three numbers that you've calculated and present the worst number. The worst in this case from an investor perspective would be the lowest yield. Option adjusted price and option adjusted yield, these are concepts we'll talk in more detail later, but here I'll give you a very high level explanation. I just said that this bond was purchased for 100, and this bond does have an embedded call option. If we remove the impact of the call option, then the bond would be worth more. Let's just say that if the call option were not there, then the bond would be worth 102. This is called the option adjusted price. It is the price which would be in effect if the option were not there. The same concept applies with option adjusted yield. Let's say that the yield when the option is there is 10%, but remember, investors don't like the embedded option. So if an embedded option does exist, investors will demand a higher yield. If that option were removed, then the yield would be lower. That lower yield, which would be in effect without the option, is called the option adjusted yield.